Hi everyone, welcome to another round of IRIS-HEP Fellowship Talks. Today we have Hector and Eric. Up first is Hector. Hector, you want to get started with your presentation?
I'm Hector. I go to Boston University, and this is my presentation on domain adaptation via histogram loss component. Okay, so in recent years, machine learning algorithms have shown tremendous promise in improving the sensitivity of results delivered by LHC experiments. While these algorithms are applied on data collected by the LHC experiments, it is often preferable or even necessary, as in the case of fully supervised algorithms, to train them on simulation. However, a common problem that arises when applying machine learning algorithms in simulation is that the source domain is not fully representative of the target domain. The source domain is a dataset used to train the machine learning algorithm, while the target domain is a dataset on which machine learning algorithm is applied. If the input features to the algorithm do not perfectly model the simulation, the output distributions may also be different between data and simulation. In a high-energy physics analysis, these differences would typically be accounted for through a systematic uncertainty, which covers a level of disagreement between data and simulation. The domain shift between the source domain and target domain refers to the problem of the training sample not being entirely representative of the sample where the algorithm will be applied. Domain adaptation, thus, refers to methods which attempt to build algorithms robust to differences between the source and target domains. Solutions are usually applied pre-training or during training. Pre-training solutions focus on transforming features in the source domain to be more representative of the target domain, while solutions applied during training typically add a component to the loss function, which rewards invariance between the source and target domains. Pre-training solutions are typically done for any high-energy physics analysis, regardless of whether machine learning methods are even used, and usually take form in correction to the simulation. So in this project, we're applying a solution during training by explicitly rewarding the DNN for minimizing differences between distributions in the source and target domains. Gradient reversal layers. Solutions applied during training are less common in high-energy physics, but have been successfully applied. Gradient reversal layers have been included in training to minimize the DNN's ability to distinguish between events from data and events from simulation. For instance, a CMS search for new long-lived particles decaying to jets utilizes DNN to identify jets originating from long-lived particles. A gradient reversal layer is included during training to minimize the DNN's ability to distinguish between events from data and events from simulations. Although applications of gradient reversal layers are not widespread, it has shown promise in the CMS search for long-lived particles. The gradient reversal layer discourages the DNN from learning features, which allow it to distinguish between data and simulation, and has shown to improve the agreement of the output distributions between data and simulation. The plots below show such improvements. The figure compares scores between data and simulation for the DNN trained to identify jets originating from long-lived particles. It shows that the inclusion of gradient reversal layer improves agreement between data and simulation and reduces the systematic uncertainty. Though the gradient reversal layer has been found to improve agreement, we have attempted to implement a more direct solution to the issue of domain adaptation. Instead of implementing a gradient reversal layer during the training of the DNN, we include a term to the loss function known as a histogram loss component. We constructed a histogram of the output distribution for both data and simulation and minimized the bin-by-bin differences by adding a histogram loss component. A histogram loss component explicitly rewards agreement between the distribution between data and simulation. With the histogram loss component, instead of discouraging the DNN from learning features, we allow the DNN to distinguish between examples from the source and target domains. Thus, the histogram loss component is responsible for minimizing differences in the output distributions for the source and target domain. We applied our histogram loss component for a classification task, which is trained on events having a label 0 or 1, and which gives a prediction on each event between 0 and 1. We estimated the probability distribution functions for events from the source domain, denoted S of S, and the target domain, denoted S of T, through histograms H of S and H of T with n number of bins. These bins are assumed to be uniformly spaced, such as the nth bin of H of T can be constructed with as the equation seen below, where delta I of n is a weight defined, such as that we linearly interpolate for each entry when constructing the histograms. A loss function rewarding agreement between the probability distributions between data and simulation can be constructed as a sum of the squares of differences between each bin of h of s and h of t, as seen below. A composite function, which rewards performance on the original task, as well as agreement between h of s and h of t, takes the form below, where L of c is a cross-entropy loss function, and lambda is a hyperparameter that dictates the balance between rewarding classification and rewarding data and simulation. That dictates the balance between rewarding classification and rewarding data and simulation histogram agreements. But before I could get to the domain adaptation component of this project, I first began by learning about classification and how to create a deep neural network. We constructed a photon ID and DNN with a simple set of features describing isolation and shower shape. The classification component is trained with prompt and fake photons from gamma burst jet simulations, while the histogram loss component takes electrons from data and simulation in a control region. For the classification component of the project, I trained the DNN on a dataset of fake and prompt photons. I split the dataset into a training and testing set, and trained and tested the DNN on the corresponding set. I calculated the AUC score of the DNN, which is a way to calculate the model's performance, as well as the DNN's predictions for the mean value of the prompt and fake photons, so I can get a sense of whether DNN served as accurate predictor for the data set. I also calculated DNN's AUC score as the number of epochs increased, and the results are as we should expect. As the number of epochs of training increase, the DNN's performance increases. So our main goal for this project was to quantify the performance of the DNN with the histogram loss component. We sought to quantify this performance in terms of the original task, which was found through the AUC score and through the data and Monte Carlo agreements. For original DNN, which we found that as we increase the value of the lambda, which represents the strength at which I implement the histogram loss component, the agreement between the distributions of the source and target domain greatly increased, but the AUC score greatly decreased as well. This figure is a plot of the DNN's AUC versus the strength of the domain adaptation component in the loss function. This plot also demonstrates the probability that the distributions in data and simulation are sampled from the same underlying distribution. The probability that the distributions from data and simulation are from the same sample are obtained through a KS test on the distributions. Thus, a higher value of p-value on the right represents a better agreement between the distributions in data and simulation. The red plot points represent the AUC score, while the blue plot points are a calculation of the level agreement between these distributions. Since the AUC is an aggregate measure of the performance across all possible classification thresholds, we want the AUC score to be as close as 1 to possible. When initially increasing the strength of the domain adaptation component in the loss function, the AUC score decreases very slightly. However, as the magnitude of the domain adaptation component is increased, we see a sharp decline in the AUC while the agreement between the distribution levels out. One of our goals as we move forward was to keep a high AUC and p-value as we increase the strength of the histogram loss function and to find out at what lambda value the model works at best. After updating DNN, I recreated the previous plot and found a much more stable AUC score as I increased the strength of the histogram loss component. However, this new iteration of the DNN had less agreement between the source and target distributions for certain lambda values. From this plot, I also noticed that the model worked best at a lambda value close to 10 to the power of 1, so we began to test different optimizers, learning rates, and batch sizes in the DNN with a lambda value of 10. After testing a batch size with a variety of magnitudes, I found that a batch size of 10 to the power of 5 was most effective since it had the highest AUC score and highest p-value score, while maintaining a low error bar in comparison to the other batch size value, which you can see in figure 2. While training the DNN with these different batch sizes, I kept all the other parameters constant so I could clearly see what effect the changing batch sizes had on the DNN's performance and trained the DNN on a large number of trainings. In the DNN, I didn't specify any optimizer in this case, so DNN defaulted to the default optimizer for all these tests. And it did this so, once again, all the tests could be kind of constant, and I could see the differences between the batch sizes more clearly. For the learning rate, On figure 4 and 5, I have two plots for the default optimizer with a batch size of 10 to the power of 5 and two different learning rates. I tested a variety of learning rates with different magnitudes, but I ultimately found that the learning rate of 3 times 10 to the power of -3 was most affected for this DNN. And the learning rate of 3 to the power of -3 is shown in figure 2, which is this one, and it shows the value with the highest AUC and p-value score with this learning rate of 3 to the power of 3 times 10 to the power of -3. And so after testing for the optimizers, I tested all the Karif's optimizers, and I found that the optimizer that best suited my model was the Atom optimizer. I tested these optimizers with a batch size of 10 to the power of 5 and a learning rate of 3 to the power of 3 times 10 to the power of -3, which I had found previously worked best with my model, and a lambda value of 10 to ensure that the DNN would have the best performance. That being said, it is possible that other combinations of these factors could result in higher performance values for these optimizers. And because I didn't test all these different combinations, I'm not too sure about that. But given these combinations, I found that the Atom optimizer was the best. So in summary, after testing the DNN's ability to accomplish its original goal, which we found that the histogram loss component applied during the DNN's training was successful in increasing the agreement between the source domain and the target domain. In summary, after testing the DNN's ability to accomplish its original goal, we found that the histogram loss component applied during the DNN's training was successful in increasing the agreement between the source and target domain. And thank you very much. Here's a link to the GitHub repository if you're interested in learning more about what we did in this project and what my DNN looks like. Thank you.
Thank you, Hector. Up next, we have Eric. Eric, would you like to get started?
All right. I'm actually, today I'm going to be talking about anomaly detection with spiky neural networks. My name's Eric. I went to Caltech last year. I'm just starting out as a PhD student at MIT, so I'm actually right down the road from Hector at BU. My mentors were Maurizio Pierini and Jean-Roch Villemain. Yeah, let's get started here. So the first thing I wanted to talk about is a comparison between computers and the human brain. So the current neural network trained with deep learning are state of the art in machine learning and artificial intelligence. Take, for example, GPT-3, which cost $12 million to train. Now let's think about how much it would take to train our own brains. So in your own brain, you have around 10 to the 10 neurons, 10 to the 3 synapses per neuron, and 10 to the 3 precision. And basically what that computes to is 600 petaflops to train our own brains how to think. And if you run this on the world's most powerful supercomputer, you can maybe get 400 petaflops, and it takes 30 megawatts to do this. And it's really interesting because our own brains only take 12 watts to run. So what is the difference between these computers and our brain? And how can we harness the differences and create more efficient algorithms for us to run on our computers? The best of both worlds are biologically based neural networks plus some kind of backpropagation algorithms that exist in the machine learning literature. So first, I wanted to start with a basic overview of DNNs, and then we'll see how they differ from spiky neural networks. So the DNN is the most common type of artificial neural networks. Basically, what you have is an input layer, which is connected to some hidden layers where you perform some kind of nonlinear computation, and which are then passed to an output layer. You are able to learn nonlinear relationships between your input data and your output data using stochastic gradient descent. And this model is based off of neurons from biological brains. And it was developed decades ago, and it's been iterated upon. But is this really how biological neurons function? We have to ask ourselves. your nodes of your DNN are receiving and combining signals with an internal activation function. That's not really what your brain is doing. They're performing a weighted sum of their predecessor nodes. That's not really what your brain is doing. And these networks only compute as feed-forward networks, right? You start with an input layer, you have to go to your hidden layers, you have to calculate every single node in the entire model to get to some kind of output. And I mean, this is simply not how your brain functions either. There are some much better, or there's a much better way that this could be done if we're trying to really mimic biological neurons. So let's think about how these biological neurons actually work. Basically, you have your neurons, which are connected by synapses to neighboring neurons. And these neurons have a kind of variable electrochemical potential inside of them. And when this electrochemical potential reaches a certain threshold, you fire an electrochemical pulse through your synapses to your neighboring neurons. So basically, that's the only way your brain is able to compute something. You basically just have your neurons firing delta functions to their neighboring neurons. So we take this to the spiking neural network regime. And basically what we do is we utilize these membrane potentials to mimic the behavior of the human brain. The structure is very similar to a DNN, but instead of performing weighted sums at the nodes, you basically add together asynchronous spikes, which are activated at a certain threshold. And then these asynchronous spikes, which are delta functions, signal the occurrence of an event. So this is the membrane potential of a spiking neuron. And basically what happens is there's nothing that happens, or there's nothing that occurs in the membrane until it reaches a certain potential. And once it reaches that potential, it spikes and it drops back down. So that's the whole computation going on in a spiking neural network. So now let's think about time series for spiking neural networks. If you look at this last plot, basically the asynchronous spike signaling the occurrence of an event is inherently temporal. So these SNNs are perfect for time series data, as SNNs are inherently temporal architectures. Basically, you're able to encode through spike timing and spike rates information, and you're able to transmit this information through the network using these neurons. And spiking computation is event-driven, which is really important. So when you have little to no information recorded, your spikes don't occur, and so the SNN doesn't have to completely compute its entire model. Remember, back to DNNs, you always have to compute every single node in a DNN. But with an SNN, if you don't see anything of importance, you don't fire the spikes off, and your model ends before you have to do much computation. And of course, when you record bursts of activity, these thresholds are met, and then spikes are propagated through the network. So it makes for a very efficient computation. So some of the benefits of spiking neural networks include analog computation, low power consumption, fast inference. You can parallelize these systems, and they're excellent with time series data, but they don't come without their problems. A lot of the packages for implementing these SNNs are experimental. It's an up-and-coming field. You have experimental chipsets to natively run these spiking neural networks, and I really think there's only one chipset from Intel. Of course, these spiking neural networks are non-differentiable because you can't take the derivative of a delta function, and so there's a lack of training algorithms. But this is definitely being improved upon, and there are some assumptions that you can make to train your spiking neural networks. And they currently don't outperform DNNs completely, but there are some regimes where they are outperforming recurrent architectures. So the project goal is to bring these SNN architectures to high energy physics applications. And the way we did that is a little interesting. Not at all, I guess, related to high energy physics. Our testing grounds was the detection of gravitational waves at LIGO. And so I'll explain why this is important, but first let's see how LIGO works. Basically, you have a laser, which is fired through a beam splitter. It travels through two arms of the detector. And if either of these arms change at all in length, when your laser recombines at the beam splitter, you get some kind of interference pattern. And this interference pattern is registered at a photodetector. But what this photodetector is actually outputting is a one-dimensional time series strain of what it's seeing inside of the detector. And so if we really want to test spiky neural networks and we want to test anomaly detection algorithms, we thought that a great testing grounds would be these gravitational waves at LIGO. Using this one-dimensional time series strain should be the most simple application for spiky neural networks. And so if it can't be done that way, then it shouldn't be able to be done with complicated high energy physics experiments. So this is an example of the LIGO data. GW170817, I believe, is the first binary neutron star merger. And this is what the data looks like at different detectors. As you can tell, it's not at all obvious that, it's not at all obvious that a gravitational wave has passed through any of these detectors. It never actually passed through Virgo. But at Livingston and Hannaford, the two LIGO detectors, like maybe you can see something, but it's very faint. And this was a powerful signal as well. There are much less powerful signals that we're trying to detect, or not we, but they are trying to detect at LIGO. So we generated some data, basically simulated typical detector noise, and then simulated different gravitational waveforms hitting the Earth with varying binary black hole masses and signal to noise ratios and at different angles in the sky. And basically you add this gravitational wave strain to the noise if you have a signal event, and if you have a background event, you just have no added gravitational waves. And the name of the game here is basically just to identify gravitational waves. But it gets a little interesting here. So the currently used methods for identifying gravitational waves, one is match filtering, which is the current method used by LIGO, and it basically compares incoming gravitational wave data to a bank of simulated waveforms that they have. And it's pretty good at identifying gravitational waves, but it can only identify gravitational waves that are available in their own banks. So if they can't simulate the gravitational wave, then they will have a hard time detecting this gravitational wave. And similarly, they are moving to machine learning techniques using convolutional neural networks on this strain data. And the same deal here. If you aren't training your convolutional neural networks with your simulated events, or if you're missing out on simulated events in your training set, it's going to be hard to detect these gravitational wave events. So what we are doing is taking an unsupervised learning approach. That means that basically we're not telling our models what a gravitational wave looks like. We're basically just going to tell our models the signature of the noise, and the models using these models are going to detect any deviations from the noise of LIGO. And so if a gravitational wave comes through, the model is supposed to get confused. So we do this with autoencoders. Basically, you send your input data, which is encoded into a smaller latent space. This is a bottleneck space. So it forces the autoencoder to pick some important information in the latent space to then decode the data back into some reconstructed data. And so these nodes can be made out of DNNs, RNNs, convolutional layers, and what we wanted to try, spiking neural networks. So I just want to iterate again that this unsupervised learning is something kind of new for LIGO. Instead of relying on simulated waveforms, we wanted to rely on just the signature of the noise and not give our model any kind of idea of what a gravitational wave should look like. And so basically what you do is you compare the input and the reconstructed data, and that gives you a model loss. So you train your autoencoder to encode and decode data with no anomalies, no gravitational waves, and then you set some threshold based on what true positive rate you want for gravitational waves. And basically you run this autoencoder on test data, which contains gravitational waves, and you identify events that fall above a certain detection threshold. This whole model is basically just supposed to get confused when anything besides noise passes through it. That's the gist of the situation. And if it gets confused, then you see a spike in your loss, in your model loss, and you can identify that as falling above a certain detection threshold. So of course you can replace these units here with anything you want. What we wanted to try, and we tried a few different architectures, convolutional neural networks, LSTMs. We also tried spiking neural units, or SNUs. Basically what spiking neural units do is they don't exactly mimic a neuron from a biological neuron, but they are kind of similar in the sense that a spiking neural unit has two neurons inside of it, one that accumulates incoming neurons and one that sends out spikes. And this accumulation neuron can talk to the spiking neuron in a kind of recurrent relationship. This spiking neuron can pass back information to the accumulation neuron. And so this resembles an LSTM sort of. So it's a type of recurrent architecture with spiking neural networks. And this SNU is able to, through certain deep learning frameworks, train with backpropagation through time. I'm not exactly sure how this works, to be honest, but somebody figured it out, and I think it's pretty impressive. So there are certain packages that can calculate this backpropagation for spiking neural units. And so this is basically what we input into our spiking neural network autoencoder. I guess I should cover that there are certain packages that can do this kind of stuff. SNN Torch and Neuro AI Kit are some recommended packages by me. And then if you want to get more in depth, you can go with Nango, which is kind of like comparing like TensorFlow to like Keras. And then SNN Toolbox is able to convert artificial neural networks to spiking neural networks. But in my case, that's kind of useless. Like I want to train spiking neural networks natively instead of converting ANNs to SNNs. So this is what the input to our SNN autoencoder looks like. Basically, you have to input your data as spikes, and then you have to compress that data, and then decode that data back into these spikes, and see if you have any differences between the input and the output data. And so here are some of the results. I compare here on the left a LSTM autoencoder, a CNN autoencoder, and a spiking neural unit autoencoder. And the results are not great for the spiking neural unit, but I think it's really impressive, honestly, that the spiking neural unit could even keep up at all with LSTMs and CNNs. That it's even in the same ballpark is pretty impressive, given the fact that these are basically just like primitive neurons that are firing delta functions. And the loss plot for the spiking neural unit was not as exciting as this LSTM autoencoder, but I wanted to show what a loss kind of looks like. And basically, you have your noise data when a gravitational wave comes in, you see a spike in the loss, and then you're able to trigger on this spike with anomaly detection methods. So of course, our unsupervised approaches will have a lower accuracy than supervised approaches in detecting gravitational waves, but the contrary is that they have a higher chance of detecting anomalous events. And so this is basically what I did for the summer. Some future opportunities with SNNs for high energy physics. SNNs live in the time domain, right? And they offer low power consumption and fast inference on neuromorphic hardware. This is something I would say is pretty important, the neuromorphic hardware part. These algorithms that I was running were not on neuromorphic hardware, so they were really not any faster than algorithms that were just using normal machine learning methods. But if you're able to utilize neuromorphic hardware, and I believe Intel has a chip called Luigi, which will run spiking neural networks, you can run really fast with really low power. You can make highly parallelizable systems. I think that this could serve as some kind of trigger in the future for LHC time series data. Now, I'm not actually sure if the LHC has any time series data. I don't think they do, but maybe with the timing layer coming online soon, that could be something interesting to check out. And of course, future advances in the field of SNNs and better backpropagation algorithms will lead to better performance than DNNs on time series tasks. I don't think they'll ever perform DNNs on casual other tasks, but for time series tasks, these are a very promising architecture. So that's it from me. Does anybody have any questions?
What's your next step at MIT? Are you working with someone there?
Yeah, I'm working with Phil Harris at MIT. He's also an IRIS-HEP, and we are actually implementing these. Well, we're doing a few things, but in terms of this project, we're working directly with the LIGO people on the next run of LIGO and their trigger for the next run. And we're not going to be implementing SNUs at all, but we are looking into LSTM autoencoders for their trigger system. In addition to their normal triggers, it could be interesting to run an LSTM autoencoder or a CNN autoencoder on the side and see if we pick up any additional gravitational waves that haven't been identified by the normal algorithms. So in terms of this project, that's kind of the next steps. One of my colleagues wants to use these spiking neural units autoencoders in something else for LIGO. So we'll see if these come up again. But I have a feeling that it's like an emerging branch of machine learning, and it'll get more prominent definitely in the future because these are very promising architectures.
Very nice. Anyone else?
Thank you, Eric. And thank you, Hector, as well. That's all we have for today. So thanks everybody for joining.
Thanks everyone. Bye. Let's talk.
Bye.
Bye.
Thank you. Bye-bye.